Good afternoon. My name is Jenna Turocy, and I work at Covidien as an R&D engineer. Today, I'm going to be presenting a new method to analyze tissue analogs. I wanted to begin with just a brief history of surgical stapling at Covidien. Covidien has been developing surgical staplers for the past 40 years. In the late 1980s and early 1990s, we transitioned away from larger, bulkier devices for open procedures to more minimally invasive devices. Now, looking at the future of surgical stapling, we are developing powered stapling as well. So an important step in developing any medical device is frequent testing to simulate device performance. Testing performed on animals is not humane, nor does it produce repeatable results due to the variability of tissue from animal to animal. A synthetic tissue may provide a viable alternative if it's able to mimic the desired characteristics of organic tissue. Quantifying the mechanical properties of organic tissue can be challenging. Soft biological tissue is anisotropic, it's viscoelastic, it exhibits nonlinear stress-strain relationships, and it's highly dependent on the time spent outside the body due to dehydration and degradation. A powered stapling device will allow us to measure soft biological tissue within its natural environment in a precise and highly repeatable method. Developing surgical staplers, we were particularly interested in the compression and penetration properties of organic tissue. We can use the feedback capabilities of a powered stapling device to compare these properties in organic tissue to tissue analogs in search of the best media to be used for testing. This is a picture of the powered linear stapling device. It was developed as a prototype. The stapler is an endo-GIA. It places 6 rows of staples on the tissue while simultaneously transecting the tissue in the center. It staples and cuts in a linear fashion that is from the proximal to the distal end of the device. Now, unlike traditional mechanical staplers, this stapler is run by a motor. So when in use, the motor draws an electric current from its power supply. That electric current is directly related to the torque in the motor, and then we can then translate the torque in the motor to the linear force that the tissue experiences as it's compressed and penetrated. For my methods, I selected my test media to be in vivo canine and porcine tissue, foams, rubbers, and other synthetic materials. While I fired a staple line on the media, I recorded the current that the motor was drawing from the power supply. The power supply would output an analog voltage proportional to the current. That went to a data acquisition system, which is an analog to digital converter. Now, we use this data acquisition system so we could have a higher sample rate. We had a sample rate of 1,000 samples per second to the PC, and that high sample rate is the reason why our method is so precise. We then had LabVIEW software programmed to format the data into graphs, and we can analyze this data, and we separated it into 3 intervals. First, when the device clamps on the tissue. Second, when the device staples and transects the tissue. And third, when the device retracts the knife back into the device. So our main parameter of measurement was electric current. And this is the graph of the electric current when the device first compresses the tissue. Again, the electric current, it's directly to the amount of force that the tissue experiences. In my graph here, the green lines represent canine and synthetic large intestine tissue, and my blue lines represent canine and synthetic stomach tissue. As you can see in the graph, the 2 lines that are behaving very similarly, the darker lines are the in vivo canine tissue, and that is because as you compress a viscoelastic tissue gradually with a linear stapler, it's also displacing the fluid within the tissue. You can see it took a larger amount of force to compress the synthetic stomach tissue, my light blue line on the top, than it did to compress the synthetic large intestinal tissue. This is the graph when the device is stapling and transecting the tissue. You can see it took a larger amount of force to penetrate the stomach tissues, the blue lines. Each peak in the graph you're seeing represents the force to form a staple. So just by looking at the graph, you would be able to see if the device was missing a staple, if there was a staple jam, or another type of misfire. I also wanted to point out that each line in the graph you're seeing represents one sample. It was the sample that was an average representation for the test media. I tested several different synthetic materials, and the synthetic material I'm showing you right here best represented organic tissue. So you can see in the graph how the dark blue and light blue lines, the synthetic stomach tissue and the in vivo canine stomach tissue, both matched up very similarly for penetration forces. This is the graph of the retraction of the knife back into the device. So you can see in the graph that the darker lines had the in vivo tissue had a smaller force of retraction. And that's because there's less friction as the knife slides against the slippery surface of the tissue. So as a result of this testing, we found a material that was primarily composed of water to be the best representation for organic tissue. This makes logical sense as organic tissue also contains a high percentage of water. We modified this aqueous material to obtain the same compression and penetration forces we saw in organic tissue. We are now expanding the testing to include other tissue types besides stomach and large intestine. We are also introducing other variables such as age, sex, and weight, and beginning to compare animal to human models. In the future, this technology may also be available in the OR. This technology can help the surgeon quantify the thickness of the stomach to help determine the correct staple size. And measuring the electric current can also tell the surgeon if the staple closing was successful and if proper staple closure was achieved. So I would just like to end by thanking my other team members, because this was not an individual effort, but a teamwork. So John Herb, Andrew Meese, Danielle Rassnett, Tom Wenchel, and the rest of the Powered EGI team at Covidien, and they're all instrumental in developing this new technology and its uses.